In this video, we're going to do a little bit more with the dot products. We already talked about the geometric definition of the dot product. There is a calculating formula that is often more useful when you're actually calculating the dot product. So this is an algebraic way to find the dot product between two vectors. Some textbooks start with this as the definition and then derive the geometric interpretation from that. So what this means is algebraic. That means the plug and chug of the computation that you're going to do here. So when I take v dot w, the algebraic or computational formula for that would be that I take the first component of the first vector times the first component of the second vector, v1 times w1, and then I add that to the product of the second component with the second component, v2 w2 plus v3 w3. Sometimes you'll see this formula written with sigma notation to represent a sum. But this is an algebraic tool that is used for calculating a dot product. There is a nice derivation in our textbook that shows how to use the geometric definition to derive this algebraic formula using law of cosines and an angle between two vectors. So it's a really lovely application of some trigonometry that you might have done a while ago. I'm not going to go through that here, but it is lovely to look at, so you should look at that in your textbook. We will use this when we're doing computation with dot products. So when you're asked to calculate a dot product, this is often an easier way to do that. But when you want to think about what your answer to the dot product means, it's helpful to go back to this geometric interpretation of what the dot product is. All right, so we are going to look at some examples here. I'm just going to write down some examples of a few vectors, and we're going to do some calculations with them and calculate some dot products, and then also think about what those answers mean. All right, so for my vectors here, I've written down some examples here that I want to use. So we're going to use -3, 5, -2 for one of the vectors, and then another vector, 2, 0, -1, and a third vector, 1, 1, 1. Okay, so I can calculate dot products between each of these vectors. So if we're going to calculate, say, u dot v, I can think about what the answer means for u dot v by thinking about the geometric interpretation of that. But when I do the calculating, I'm just going to do this, which is multiplying the corresponding components and then adding up all of those answers here. So -3 times 2, we'll get -6, plus 5 times 0 is 0, plus -2 times -1 is 2. So I'll get -4 for this dot product. Okay, so in the last video, we talked a little bit about the geometry of dot products, and that when that dot product is negative, that tells you something about the geometry of those two vectors. So this dot product is negative. I got that from using the computing formula, but when I think about that in terms of the geometric definition, that tells me that the cosine of the angle between the two vectors had to be negative, so that those angles form an obtuse angle. U and v form an obtuse angle because I got a negative answer for the dot product. This is the only part of this geometric definition that could be negative. All right. If I calculate, let's do v dot w here. All right, so v dot w, I will get 2 times 1 is 2, plus 0 times 1 is 0, plus -1 times 1, -1, so I get 1 for that dot product. All right, so that, I got a positive dot product, which tells me that my vectors v and w form an acute angle. Again, talking about what we talked about last time, with the only part of this that could be positive or negative changing signs would be this part right here. All right, let's do one other dot product here, u dot w. All right, so when I do u dot w, I get -3 times 1 is -3, plus 5 times 1 is 5, plus negative 2 times 1 is negative 2. And so I get 0 for that dot product. So that tells me something about the geometry of u and w. U and w are orthogonal vectors because they have a 0 dot product. And in that last video, we talked about orthogonal vectors, that there are really 3 ways 2 vectors can be orthogonal. One is if one of the vectors is the 0 vector, or if the other vector is the 0 vector, or if they form a 90-degree angle. Neither of these vectors, none of these vectors here are the 0 vector, so that means that these 2 vectors not only are orthogonal, but they also form a 90-degree angle. They're obviously not the 0 vector. They don't have all their components being 0. All right, so one of the applications that you will use for dot products, there are several, but one of them that you will use is just finding the angle between 2 vectors. We use these dot products to talk about obtuse, acute, and 90-degree angle, but if I want to actually find the measure of the angle between 2 vectors, I can use this formula here. Our textbook also has this formula rewritten and solved for theta. I find that formula a little bit more difficult to remember. I tend to just remember this formula, and then I can do the algebra in my head to solve that formula for theta. So we'll go ahead and find the angle between vectors u and v, and then the angle between vectors v and w. We already mentioned that the angle between these 2 vectors is going to be 90 degrees because I got a 0 dot product, and neither of them is the 0 vector. All right, so if I want to find the angle between u and v. All right, so I'm going to use this formula with u and v, and I'm going to solve for theta. So you can do that algebra in your head probably. Theta is going to be cosine inverse of the dot product, but not v and w that are here in the formula, between the 2 vectors that I'm working with here, u dot v, divided by the 2 magnitudes. So the magnitude of u and the magnitude of v. All right, so I just need to do those calculations. I've already calculated the dot product over here, so we'll just put that number into this formula, and the magnitudes of the 2 vectors are not difficult to calculate either. So cosine inverse of the dot product is negative 4, and then the magnitude of u, so I will have the square root of 9 plus 25 plus 4. So 9 plus 25 plus 4, square root of 38. And then square root of v, the magnitude of v would be square root of 4 plus 0 plus 1, so times square root of 5. All right, if I want my answer in exact form, maybe I just leave my angle written like that. If you want an exact form answer for your angle. If you want a decimal approximation for your angle, you can do that as well. You can get out your calculator, make sure you know whether you're in degree or radian mode so you know what kind of angle you're getting here on your answer. Let's see here. I am not sure I have the right answer written down on my paper here. So I don't have my answer written down on my paper, so I don't know what the decimal approximation is there. But you can get that on your calculator. You should get an angle that is between 90 and 180 degrees, or you should get some angle in radians that is between pi over 2 and pi radians. So you can get that on your calculator. Also, if I want to find the angle between, let's see, what was our other one? V and W here. All right, so we're going to have that angle is going to be cosine inverse of the dot product of V and W. So that is 1 over the magnitude of V, so that will be square root of 5, times the magnitude of W, so the square root of 1 squared plus 1 squared plus 1 squared, so square root of 3. All right, and again, you can leave it in that form if you wanted an exact form. If you want a decimal approximation, go ahead and get your calculator out and get that decimal approximation, and that's perfectly fine, but this is fine for an exact form answer. All right, we'll look at some more applications of dot products in the next video.